you a few examples of 8085 programming. The first example that we will look into it is a program to count number of ones in the content of D register, and we want to store the value in the B register. So, our D register contains some number, say so this is the D register, then the content may be say 1010 1111, and we want to count the number of ones. So, in this case the answer should be 6. So, how do we do it? So, first this B register, since the B register will be holding the final value. So, we are clearing the B register. So, B register made equal to 0. Then in the C register we take it as a some sort of counter, like how many bits we have considered so far. Okay. So, basic idea is that, so we will move this B register content into A register. So, sorry, so this D register content into A register, and then we will check what is the value of this least significant bit. And for the technique for checking, there can be several ways by which you can check the content of this least significant bit. One possible way is like this. So, you have the carry flag. So, you do a rotation. So, rotation like this, and this carry flag comes here to the most significant position. So, this is the bit D 0 and this is the bit D 7 of the A register. So, if this bit was equal to 1, then after this rotation the carry flag will be equal to 1. So, we can check the status of this carry, and after 8 such rotations, so we will have the count, we have already seen all the ones in the B register. So, the program is like this, that we we move the content of D register to A register, then rotate accumulator right. So, this rotate accumulator right. So, this does exactly the thing that we are looking into, the D 0 will be coming to the carry bit, and the carry bit will come to the D 7 register. Then jump on no carry. So, if the carry is not set, that means the corresponding bit was reset, the bit D 0 was reset. So, we jump on no carry to skip. So, there we do not increment the value of the count B, but if the carry was set, then it will come to this point INR B, and then the B register value will be incremented by 1, and it will be counting that that 1 it has seen, okay, that 1 bit that it has seen. And then it will decrement the C register, because we have already seen, we have already checked the value of 1 bit. So, it will be decrementing the C register, the C register will become 7, and then till C register becomes 0. So, it will be jumping back to it will be jump on not 0 to this back this point, and then again we are rotating the next bit. So, by the first rotation what has happened is, so the bit at position D 1 has shifted to D 0. So, in the next rotation this bit D 1 will be coming to this carry bit. As a result, we can again check the carry, and then we can take a decision whether bit D 1 was equal to 1 or not. So, this way we can count number of ones in the D register and store the value in the C register, in the B register. Next, we will be looking into another program that will sort a given 10 numbers from memory location 2200 hex in the ascending order. So, from 2200 hex we will have 10 numbers, and then those values will be sorted. The sorting algorithm that we will use is basically whenever we find two numbers out of order, we exchange them, and this process we repeat for all the 9 entries, and that way it is done. So, how are we doing it? So, first this B register is having the value 09. So, this B register is holding the counter. Then, so we actually need two counters. So, this B register is any loop comparison. So, you know that any sorting algorithm, it uses nesting of two loops, the bubble sort type of algorithm. So, it uses nesting of two loops. So, here exactly what we have done here. So, for the first loop the counter is in B register, for the second loop the counter is in C register. Then this LXI H 2200 hex. So, this is the 2200 hex value is loaded into the HL pair, and then we get the first number into the A register. So, from 2200 onwards we have these numbers stored. So, if this is the location 2200, the very first thing that we need to do is to check the contents of 2200 and 2201, and if the numbers are out of order we need to exchange them. So, my HL pair is now pointing to this location 2200 by means of this instruction, and then move a comma m. So, whatever be the value, suppose the value was 10. So, the A register is having the value 10 now. Then INX H, now the HL pair is moved to this point. Okay. So, HL pair points to this, the next entry, and then compare memory. So, this 10 is compared with the next one. Suppose the value here is 5. So, 10 is compared with 5. So, if it is less, then jump on carry. The jump on carry means the number memory, the location, the value at the next location is larger than the accumulator. Otherwise, if the number is smaller than the accumulator, which is the situation here, then the carry flag is not saved or is not set. So, jump on carry and jump on 0. So, they will be checking whether it is less or equal. If it is not so, then we need to interchange between these two memory locations. So, here actually that is the situation. So, for that purpose we move D comma M. So, D register gets the value 5 and then move M comma A. So, memory is pointed to by HL and A register value is 10. So, at this location we get the value 10. Then in the next then in the next point what we are doing, we are decrementing H. So, that this HL pair was pointing to So, this HL pair was pointing to So, HL pair was pointing to this location, and then this DCX-H. So, DCX-H will take the HL back to this point, the previous point, and then we are doing move M comma D. So, move M comma D will put this 5 value into this location. So, as a result, so these two values are interchanged. So, then we are doing INX H. So, H the HL pair points to this, and then we are decrementing C. So, second counter value is decremented and we are checking whether the first loop should end or not. So, J and Z jump on not 0 back. So, it will be going back to the location, it will be going back to the location back here if the count value is non-zero. So, this C register value has become non-zero. So, that way this will be continuing the loop. So, now it will compare so the next location. So, it will compare the next location with the next entry. So, as a result this loop these two loops, when they are repeated 10 times in that is 9 into 9, that is 10 times each loop will be executed, then all the numbers will get sorted. So, this is basically the bubble sort type of algorithm that we can implement in 8085 program. Next, we will be looking into another program that will calculate the sum of series of even numbers from the list of numbers. So, we have got a list of numbers and then we are interested to sum only the even numbers from there. So, odd numbers will not be added. So, the check for the odd number is that the least significant bit is equal to 1, and for even number the least significant bit is equal to 0. So, the number of numbers is stored in the location 2200 and then the actual numbers begin from the location 2201. So, for the program we just we first load this accumulator with the content of the location 2200. So, the count value is available in the A register, that is moved to C register. So, the counter is initialized to C, and then B register. So, that is initialized to 0. So, B will contain the full sum. So, that is initialized to 0. So, the HL pair they should point to the successive numbers, since the numbers start from 2201. So, HL pair is initialized to 2201. Move A comma M. So, this will get the first number into the accumulator, and then we AND immediate with 01 hex. So, that way the bits 1 through 7. So, they will be maxed out, only bit 0 will remain, because they will be ANDed with this 01. Then if that bit is if that bit was also 0, then this jump on not 0 will fail, that means the number was even. But if the number is odd, then this J and Z will be successful and in that case it will be it will not increment the sum value and it will come to this point. But if the number is an even number, then this check will be will be a failure. In that case, this we will get the number into we will get the B register content into A register and then we will be add M. So, this is basically with the previous sum we are adding the current even number and then storing back the result to the B register, move A B comma A. So, this will store the result of this addition into the B register. Then we increment H, decrement the C register and then JNZ back. So, if the C register value has not become 0, that is all the numbers are not checked. So, it will be jumping back to this position and finally, the number the added values. So, they will be stored at the location 2210 hex. So, this way this program is doing the addition of only the even numbers from a series of numbers. So, we can find out we can write this type of programs in 8085. So, whatever you have got whatever program you can think about in high level language. So, they can be written in assembly level or we can take help of some compiler and assembler to convert the high level program into assembly language program. The advantage of the assembly language programming will be you know the exact size of the program, you also know the exact amount of time that will be taken for executing this program. So, if you consult the 8085 manual, then you can find out the individual number of bytes needed for individual instructions to compute the size of the program, and you can also find out the total number of clock cycles needed by individual instructions. So, you can trace through the algorithm, trace through the program and compute what will be the exact time needed for executing this program using 8085. So, that is how that is why we can take help of this assembly language programming. Next, we will be looking into another program which will be converting a packed BCD number into an unpacked BCD number. So, packed BCD number is like this, say suppose we want to so we have the number say 98. Okay. So, this 98 is stored in the location 3000, in the memory location 3000 this number 98 is stored. Now, this is stored in a packed BCD format. So, BCD stands for binary coded decimal. So, if you take any decimal number say 45, then it consists of 2 decimal digits 4 and 5. Okay. So, one possibility of storing these numbers is that you code this 4 into binary number. So, 0100 and code this 5 into binary number. So, that is 0101. So, this number, so this is a BCD number, BCD coded form of the decimal number 45. So, we can instead of converting this into binary number, so we can store them in the BCD format, binary coded decimal format, and this has got several utility while you are particularly displaying some decimal digits onto some display. So, this format is often useful. So, many a times what happens is that we store 2 BCD digits per memory location. So, if you memory locations are generally byte organized. So, per memory location we store 2 BCD digits, but in the application. So, it may be required that we access them individually, each BCD digit we accept individually. So, that is known as the unpacking of packed BCD number. So, when they are stored 2 BCD number per 2 BCD digit per 8 bit pattern. So, that is called a packed BCD notation, and when you are giving entire 8 bit for one number, that is when you are converting, say for example, this 98 when we are converting into 09 in one first byte and 08 in the second byte. So, that is the unpacked BCD number. So, how do we do this? So, you see first in the assuming that the number is 98 hex. So, we first move this and it is stored at the location 3000. So, LDA will get the number into A register. So, A register is now holding 98. Now, that is moved to B register, and this in the C register we move the value 04. Okay. Now, we do an AND immediate F0. So, if we do AND immediate F0, then F is 1111 and 0 this is 0000. So, this is ANDed with 98. So, 9 is 1001 and 8 is 1000. So, if you do an AND immediate, so you will get 1 0 0 1 0 0 0 0. So, you get the value 90. So, you get the first digit of the BCD number. Now, we have to, but we have to get this, we want to get 09 from here. So, for getting 09, so I have to rotate this right by 4 positions. So, this is exactly done in this part of the program. So, RRC, will shift this thing by 1 bit position. So, this 0 will come, so this 0 will come to the most significant position, then it will become 1 0 0 1 and then 3 zeros. So, it after 1 RRC, so we will get the content like this. Then we decrement C and jump on not 0 to L1. So, that means the C value has been initialized to 4. So, it will do 4 such rotations. So, after 4 such rotations, so I will get the content as 0 0 0 0 1 0 0 1. So, that is 09. Then we store the value at memory location 3001. At 3001, we store the value 09. So, this is stored at location 3001. And then we have to do the similar thing. Now, we have to get the value 8. Okay. So, B register was already having the value 98. So, we are again getting the value moved to A register, and now AND immediate with 0f. So, this 1001 1000. So, if you AND immediate with 0f, so you will get so these 4 bits will become 0 and this will become 1000. So, you will get 08. So, now we do not have to rotate anything because this is 8 is already in the least significant position. So, we just store the number in the location 3002. So, this way I can unpack a packed BCD number into individual digits. So, this is another example. So, this way there can be innumerable number of programs that you can try out in 8085 assembly language. So, there are some more important some other important instructions that we might not have covered in our course, but you can just have a look at them in any manual for 8085. Some of the interesting instructions that we have is, one is ADC. So, add register to accumulator with carry. So, we have got the add instruction which does not take add the carry into the number, but when you have got multi byte addition, so then in that case this add with carry may be essential. Okay. So, this add with carry, so this also adds the carry bit, like if you say ADC B. So, what we mean is A will get A plus B plus the carry flag, and this carry flag will be the least significant bit. So, this A and B, so they are 8 bit values, and this carry will be converted into an 8 bit value like this, and this is the carry. So, whatever be the carry, so that will come at the least significant position, and that will form another 8 bits. So, those 3 bits will be added. Then there is another important instruction which is CMC or complement carry. So, complement carry, so this it just complements the carry. So, if the carry was 0, it becomes 1, if the carry was 1, it becomes 0. Then there is another instruction which is known as DAA, which is decimal adjust accumulator. So, it is for converting one 8 bit binary number into 2 4 bit BCD digits. So, it is for you can say that converting one binary number into the BCD number. So, DAA is an instruction for doing it. So, if in our digital circuit combinational circuit classes, so you have seen that if for converting one number to BCD, so we need to add 6 if the number is greater than 9, because if the number is say for example, if the number is say 10. Okay. So, in binary notation, if I use an 8 bit notation, so this will be stored as 0 0 0 0 1 0 1 0. Now, you see that when I am converting it into BCD notation, so what is required is that this number will be converted to 1 and 0, that is 0 0 0 1 in the first 4 bits and 0 0 0 0 in the next 4 bits. So, that is what we want, and then this can be done by doing the logic is that when this part of the number is becoming greater than 9. So, we have to add 6 to it. So, this number is 10. So, 1010. So, with that with that if we add 6. So, that is 0 1 1 0, then the number will become 0 0 0 0 and then 1 and these 3 bits remain 0. So, you get this 1 0. So, this way we can get the number as 10. Okay. So, when the number is greater than, when these least significant 4 bits are greater than 9. So, we can just add 6 and get the number. So, this way this decimal address accumulator. So, this is useful when you are converting a binary number into BCD number. Then there is a double addition or DAD instruction. So, that is for adding register pair to HL. So, this register pair value. So, you can say like DAD D. So, this HL pair will get HL plus D. Okay. So, this is the DAD instruction. The IN instruction. So, for with this we have already discussed for getting some data from some input port. So, you can use this IN instruction. Then there is LHLD instruction. So, LHLD with some address. So, in that case the L register gets the content of the memory location which is pointed to, which is given in this address. For example, if you say like say LHLD 1000, then content of memory location 1000 will come to this content will come to the L register and the content of memory location 1001 will come to the H register. So, this way we can get this LHLD. So, this will load the content of 2 memory locations into HL pair. Then we have got SHLD instruction. So, which is just the opposite of LHLD. So, instead of loading the HL pair, so it will be storing the value of HL pair into the corresponding addresses. Then there is another very useful instruction which is known as PCHL. So, this PCHL instruction, the program counter is loaded with the value of HL register pair, and this is very much useful when you are trying to execute some other program, particularly from the operating system's point of view. This PCHL is very much useful. For example, if I have got say in my memory my program, so the user program starts from location 3000 and the OS part is loaded up to the location. So, this part is got OS. Now, how does OS transfer the control to the user program? So, this can be done by means of this PCHL instruction, because for executing this user's program, so somehow the value 3000 has to go to the PC register. Now, how will it go? So, it is there is no direct instruction to load the PC register. So, what the program will do, it will what the operating system does is that it once it knows that the start address is 1000, somehow in the HL pair it loads the value 3000 and then it executes the PCHL instruction. So, that PC now gets the value of this HL pair. So, we get this PC value. So, this now once the PC has got the value 3000, so it automatically starts executing from this point. Similarly, we have got this SPHL instruction in which the HL pair is saved into the stack pointer. So, the stack pointer is loaded into the HL pair. So, this is another PC register and SP register, they cannot be loaded directly. So, we can load it through the HL register pair. Then there is an exchange instruction. So, that exchanges the HL value with the DE value. So, this is also useful in some cases. So, this is exchange. So, there is no other operand. So, it just exchanges the value of HL with the DE, and we have got XTHL instruction. So, it exchanges the HL register with top of the stack. So, top of the stack content is exchanged with the HL pair. So, this way these are some of the other instructions that we have for 8085 programming. So, if you are so whenever you are some of these instructions, as we have seen, so they are more relevant when you are considering system programming into consideration. For example, when you are this instruction like PCHL, SPHL, then XTHL. So, these instructions are useful when you are considering system programs. On the other hand, this ADC, this ACMC, this type of instructions are useful when you are doing some computation. and if you are having some decimal interface with your system, then this DAA instruction is useful, that is for converting any number into its BCD format. And for unpacking, we have already seen another code which can unpack a BCD number, packed BCD number into unpacked BCD number. Okay. So, you can refer to any book on 8085 that has got this whole discussion on this programming and all.